Very important equation for an inclined plane without friction, a icy hillside, a ramp that a cart is going down like in lab. The acceleration of the object is not g. It is g sine theta, where theta is the inclination angle of the ramp. That's it. That's all you need to know. Once you know the acceleration of the cart, of the bobsled, of the sled, or whatever, you could solve any other problem with all the techniques that we did before. That's all you need to know. That's the only piece of information. Now, there are no problems about forces on this homework, so I figure what I'll do is next week is review week, review day on Monday, exam on Wednesday. So what I figure I'll do is give you homework practice with extra force problems then, so you can practice the concepts that we're doing today, yesterday and today. Also, yesterday class, oh, my notes are so good. Oh, yeah. I can't say that with straight face. Well, I can't say anything with a straight face. Hey, get it. I've got a lovely slide set that goes over these concepts. This is a very fluffy conceptual basis. Not to say it's easy. There are lots of pitfalls here. But we're going to revisit the same topics, this time with graphics and less wordies. And more me being able to look at your answers on the Google Sheet. So everyone got Google question A was, how cute are my kids, right? Yeah? Okay, now let's move on. Yeah? And remember, that is the one and only question that is 4 points. That's actually most of your grade this semester. Just funning ya. Just kidding. Okay, so I'm going to start where I left off last time and then move backwards, try to get a deeper understanding. I claim that the essence of force, the essence of dynamics, the big idea that we're going to spend a month on is interactions, how objects interact. And the big dealio about this is we spent a month learning how things move. Now we're going to talk about why they move. By interaction, I mean something that exists between one thing and another. There are a pair of forces acting on those two objects. I want to emphasize some wording in here because I mean this particularly. An interaction, a force between one thing and another. How many objects do you count? 2. Exactly 2. Like I started last time's preview of the third law, you cannot exert a force on yourself. You cannot move your own center of mass by pushing on yourself. You cannot fly by lifting your foot. So every force involves 2 things. What does it take to be a thing, by the way? Lickable. You must lick it. No. Please don't, in general, lick it. It must be lickable in principle. Okay, so an interaction is between 2 things. Can a force be 3 things? No. For instance, Morse code paddles are sitting on top of paper towel roll, are sitting on top of the table. How many forces is this interaction here? 1. There is 1 interaction between Morse code paddles and a roll of paper towels. Is the table involved in that? No. That's a third object. There is a separate force of the table on the paper towels. That is a separate interaction. You cannot say table exerts a force of paper towel on Morse code paddles. No. 2 things and 2 things only. Yummy. Question. You can have multiple forces acting on an object, but each individual force involves 2 objects and 2 objects only. So if I actually do the do the thinking through, in this example, top exerts a normal force, a support force on the bottom, and bottom exerts a support force on the top. That's one Newton's third law pair. The table exerts a support force on the towels, and therefore the towels push down on the table. Note, there's more than one force on the towel, But those are not third law pairs. That is not a Newton's third law situation. This table is pushing up on the towel. These paddles are pushing down on the towel. That's not a third law pair. Why not? Three objects. Table, towel, paddles, not a pair. Not a third law pair. Not action and reaction. Oh, I hate that phrasing. I'll actually say that in a minute, but whatever. If I push on the wall, do I care about Earth's gravitational or the planet as a whole? No. There is me and there is wall. Okay. So now Newton's third law says whenever one thing interacts, pushes, exerts a force on a second thing, the second thing pushes back. Very importantly, equal strength, equal magnitude, but the opposite sign, the opposite direction. So if I've got a downward, a negative force of paper towel pushing downward on the table had better darn well exert a positive, an upward force on the towels. How do you feel about this? It's simple to state, but we'll do some examples. And I bet dollars to donuts there will be at least a few goofs. It sounds easier than it is. You're really happy with this? Okay, Google question B. Here is B. Take a vote. A soccer player kicks a ball with 1,500 newtons of force. How hard does the ball push on the foot? Where does that go? This is Google question B, not C. Put it in the right spot, please. My dudes. Okay, take your best shot. Time's up. Chop, chop. Okay, as I just said, sounds simpler than it is, and indeed, about a quarter of the class is missing here. Let's go back to the previous slide. What does that say there? Does that say bigger? Does that say smaller? 1,500 is equal to 1,500. Correct answer is B. B. Is that weird? Well, yeah, first question. Opposite direction. So the magnitude is 1,500 newtons. The direction is whatever direction the ball didn't go. Okay, so. I want to emphasize this here for a second. If you have a reaction force, you are guaranteed they're equal. That does not mean that any old two forces are equal. It does not mean that any old forces are equal. For instance, I exert a support force on this roll of paper towels. The planet exerts a downward gravitational force on these paper towels. Are these equal and opposite? Have a vote. Are the forces that I exert on the towels and the planet exerts on the towels, are they equal? Are they pointing in opposite directions? So are they equal and opposite? Therefore, are they third law pairs? Google form D, let me see you vote. Take a stand. Have I just told you, Google form C, yeah, whatever. Google form C. Is my hand on the towel a Newton's third law pair with the planet pulling down on the towel? Yes or no? There are two forces on this paper towel. They are equal. They are opposite. Forces are, my hand exerts a support force, also called a normal force, upward on the towel. The planet exerts a downward gravitational force on the towel. They are equal. They are opposite. Does that make them third law pairs? Is this an application of the third law? Okay, so the forces are equal. The forces are opposite. And now I want to go back a couple of slides. How many objects are there allowed to be if we're talking third law? Dose! How many objects are there if I'm talking about the Earth pulls on the towel and the professor supports the towel? 3 objects. These are not a third law pair. Okay, what is the third law pair? I push up on the towels. Earth pulls down on the towels. I guarantee that's not a third law pair. So what is the equal and opposite reaction? Let's do an example. The Google Form D. Take a stab at it. Think about it. They identify the 2 objects interacting. And A pushes B, B pushes A it. I support the paper towel with a force I call normal force or support force. I push upward on the towels with a support force. What do you identify in a short phrase as the third law pair to that? Google Form D. Again, the question is, I do want to find the third law pairs, and I claim that there is another force which is equal and opposite in this room, right in front of you, right in front of your eyes, if you can learn to see it. The opposite and equal force to the original force is my hand supports the paper towels. Now, what's the third law pair to that is guaranteed always to exist? Yes, 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 no, no, yes, mixed. Okay, by the way, what did we just discover is not the answer? Reflect on this, my grasshoppers. What did I just tell you 10 seconds ago is not the answer? Turn to your neighbor and discuss what the answer isn't. Okay, so about half the class said gravity. What 2 objects are interacting with gravity? What 2 objects are interacting with gravity? Hint, hint, hint. The planet? No, silly. The planet and the paper towel. I'm asking about third law pair between what other 2 objects? Me and towel, okay? The Earth is a third object. Cannot be the answer. Gravitational force, weight force is not the third law pair. Okay, let's do this one piece at a time. Google Form, I'm going to show you how to build it up as a step-by-step process. Question E, what 2 objects are interacting when I push upward on the towels? What 2 objects? What 2 lickable, in principle, things are interacting? Thank God. Good. The answers are professor and paper. Okay? Now let me ask you this. If A pushes on B, professor pushes on paper, fill in the freaking blank that we just said. Instead of saying one object and another, instead of saying one object and second object, repeat this sentence. Whenever professor exerts force on a paper towel, fill in the blank in the Google form. One object, second object, fill in the blank. Yeah, we're on F. Yes. Okay, just saying paper towel is not a force. To identify a force, what I'd say is name the force, say what causes the force and what feels the force. For instance, every example I've been giving, let's talk about the weight force for half a second. I've been saying the gravitational or weight force of the planet on the towels, right? I'm talking about the kind, the cause, and the feeler, the dealer and the feeler, if you want to be silly. So just saying the paper towels is not telling me a force, it's telling me a lickable object. Again, my question for you here is we have identified that professor pushes on towels are the two objects interacting. Now fill in the blanks in the sentence. Instead of one object, pretend it says professor, exerts a force on it. Instead of second object, pretend it says paper towels. Then rewrite the second part of the sentence. What does Newton say? Okay, so hand and gravity and paper towel or paper is not filling in the blanks in the sentence. I'm asking you to rewrite these words here, except identify what the first and second object that we just said are. Then you will get to the correct answer. So please, if you wrote one-word answers, you didn't do what I told you to. You are allowed to edit response and change your answer now. Okay, we're at 10 people wrong, but that's 90%. I'll take it. Question me. No, your hand is, okay, pointing. So the correct answer that I was looking for this question is to be able to say whenever a professor exerts a force on a paper towels, the paper towels exert an equal and opposite force on the professor. Okay, now think about what that says. The paper towels exert a force on the professor. To identify the force, flip the cause and the effect. What causes the force on the effects on the force, flip those around. Like we've been saying, if A pushes B, B pushes A. If Tucker support forces towels, towels support forces professor. It's sort of silly to say support. That name support suggests holding it up. This is not keeping me up. The floor is. I would call it normal force in this context here. Because it's a normal force downward on me. Okay, so the third law pair, put her together. I just told you the answer. Can you spit it back to me? Google form G. Name the kind, cause, and effect of the force. To fully specify a force, you say the kind of force, the thing that makes that force, and the thing that feels that force. What are we talking about here? The third law pair, 2. The normal force that the professor exerts on the towel is... I just told you the answer. Can you spit it back? Okay, I'm not asking you to repeat the previous line, please, and I'm not asking you to tell me properties of it. I'm asking you to tell me the kind of force, the cause of the force, and the feeler of the force. You put that together. For example, the friction force of the table on the bag. I've talked the kind, friction, the cause, the table, the feeler, the bag. So now third law pair, this. Give me, and I just told you the answer. Think back. What just happened? The normal force of professor on towels is 1. Now identify the reaction to that. The normal force that Tucker exerts on paper towels is what I'm giving you. I'm asking for the third law pair. Can you flip what causes and what affects A on B becomes B on A and say it in a phrase? Hmm. Getting better. Still not there yet. And I'm really walking you through this step by step. Okay, so here we go. All you have to do is flip two, not words, but nouns. Normal force of the hand on towels. Normal force is the kind, hand is the dealer, towels is the feeler. This is A, this is B. If A pushes on B, then fill in the blank. What kind of force? What exerts that force? What feels that force? Let's have this in a new line so I could see. I just want you to tell me the name of the force. This is Google question H. Name the force by telling me the kind of force that the blank exerts on the blank. Okay, the normal force is not the three things I asked for. I asked you to tell me three things. Google question H, tell me the kind of force that object, fill in the blank, exerts on object, fill in the blank. And again, the original force is the force that professor exerts on towel. The reaction to professor on towel is not professor on towel. You're telling me if A pushes on B, then A pushes on B. That's not the third law. The correct answer is, again, the question was normal force, original force is normal of hand on professor. And if I switch the two nouns, it becomes normal of towels on professor. Same kind, opposite cause and effect. You just flip it. You just flip it. You're making it too hard. So this says that if I'm supporting the towels are pushing down on me. Yeah? I feel them, right? Okay. Google form, let's check you'll understand in here. Can you do the exact same thing? Google question I call the force of gravity weight. I say, whoa. I say, whoa. I say that the planet exerts a weight force on the towels. Can you identify the third law pair to the fact that the planet exerts a force on the towels? A weight force on the towels. You may use your notes because I also told you this last time too. And again, I'm looking for three words here, not one word. Kind, cause, feeler. It's the same thing as what I just told you, except for the cause and the feeler flipped. The weight force of the planet pulling on the towels is the original. It can't also be the answer to this question. If you put weight force planet on towels, that's what I asked. That's not the answer. That's the question. What is the pair to the fact that the weight force of the planet on the towels is a force? Find the reaction to that. Again, the gravitational forces of the planet on the towel is the question. That's a force that I want you to find a reaction to. Okay, let's practice this. If I say switch two nouns, the two nouns are planet and paper towels, where does the word normal come from? I have a whole bunch of people telling me there's a normal force on this. Well, I mean, there is. But if you switch two nouns, A on B, B on A, planet on towels, towels on planet, that doesn't mean you change the kind of the force. Look, I'm taking away the normal force. There is nothing touching the paper towels. There is no normal force. I didn't break the third law. There is still a force pair going on as this flies through the air. It's a weight force. It's not a normal force. There is no normal force when it's flying through the air anyway. Okay, so don't tell me that the third law paired to a weight is a normal. It's not. It's always the same kind of force. Always, always, always. You don't switch that word. You only switch the cause and the effect. The correct answer for I is, I asked you if a force is the fact that there's a weight force of planet on towel, the reaction is the weight force of towel on planet. Not normal. Not planet on towel. That's the original. This gravitates that thing upward. Okay. Third law pair. One more. Professor pushes on desk with what I call a normal force. The professor exerts a normal force on the desk. Find the third law pair to that sucker. Professor exerts a force, a normal force on the desk. Tell me the third law pair. A professor exerts a normal force on a desk. Can you identify not the names of the objects? I want a kind, a thing that pushes, and a thing that is pushed. Again, professor exerts a normal force on the desk is the original. It can't also be the answer. Professor exerts normal force on desk was what I gave you. Now find the pair to that. All you have to do is switch the nouns, dudes. Mostly perfect, though. Mostly perfect. Earth's gravity in the chair is incorrect. That's a completely different force with two completely different objects. Good. Mostly perfect, though. Let's move on, and I'm going to test you again on this, and this will be a big part. Identifying the third law pair is going to be a big part of where we're going, but we'll move on for now. I'm going to skip over the action and reaction terminology. I hate these words. You may have heard them before. Theoretically, there's a benefit to being able to connect with previous knowledge, but no, screw it. When you see reaction, I want you to replace that with the word third law pair. A reaction is a third law pair. A, B, C, D, I step off a curb, Earth pulls me downward. Google question K, what is the third law pair to that force? A, B, C, D are your choices. 10 is incorrect. Don't worry about it. As long as you're answering more than half, you're perfectly fine. Okay, ready? We're now at 75% correct. We can get better than that. Okay, I want everyone in this room to be able to read the phrase with two different nouns switched. Turn to your neighbor and say this sentence, except switch the word earth with you. And also downward switches direction because equal and opposite direction. Okay, so all you got to do is turn to your neighbor and say this same sentence, flipping the word earth with you and the direction. Not toward. There's no toward there. There's no word toward. I'm just switching the order of words. Downward. You pull what? Upward. Yeah, right now I'm talking about magnitudes and we indicate the direction explicitly. If you're doing with a computation, yeah. If one is positive, the other will be negative. Okie dokie, here we go. I get to reread the sentence aloud, except I get to switch the word downward to upward. Opposite direction, and I can switch the AB into BA. When you step off a curb, you pulls earth down upward, for God's sake. You pull earth upward. What's the correct answer? C. As we say in Spanish, C. It's right there. Think about this. You pull earth upward. What kind of force is this? Weight force. It's a gravity. It's not just that yo mama pull on the earth gravitationally. Everything attracts everything else gravitationally. However, you may notice that when you step off the earth, step off the curb, unless I'm talking about yo mama, then, okay, I'll stop that. No, I won't, but I'm going to try to stop that. You may notice that the earth does not appear to recoil. Why is that? Earth is huge. If the mass is big, the acceleration is proportionally tiny. I'm going to skim over that. If the mass is big, we have a fraction. This is the second law. If you have a bigger downstairs to a fraction, you have a smaller fraction. If you have a smaller downstairs to a fraction, you have a bigger fraction, right? You guys know about the third pounder? You guys know about the third pounder? Burger King lost a lot of money because they advertised that they were going to one up the quarter pounder by giving people a third pounder. People didn't buy it. And the study focus group said because people saw 3 is smaller than 4, a third pounder must be smaller than a fourth pounder, a quarter pounder. Yeah? Reflect on this. As downstairs of fraction gets smaller, fraction gets bigger. So if you have equal, assuming the upstairs is the same, so if the upstairs is the same, equal forces as guaranteed by the third law, pushing an equal amount of force on a big object versus pushing an equal amount of force on a little object, the big object doesn't move as much. And the Earth is something like, oh God, I forget, it's like 32 orders of magnitude. One with 32 zeros after it times bigger than you. Same force exerted on a small mass produces a proportionally larger acceleration. That's why we don't notice the Earth recoiling when we step down. Okay, let's see, Google form L. Can you apply that concept to a cannonball? You just need to put a letter, yo. You don't need to type it all out. When I say ABCD, you could just tell me ABCD. Okay, you pulled the earth upward, has nothing to do with cannonballs, peoples. Read the question on the board, please. I swear, sometimes. Let me go back for a second to Newton's second law. F over m equals A. Force divided by mass is equal to acceleration. Let's consider this option D. The ratio of force to mass is the same. If the force divided by mass is the same, what is the same on the other side of the equation? Acceleration. What did I tell you up here? Did I say the accelerations are the same? This should be a hint that D is wrongo. D is exactly the opposite of correct. If I push with an equal strength on a smaller object, I'm not pushing with a bigger strength on a bigger object. Not what it says. The correct answer here is C. The cannonball goes flying. I'm assuming you're not in Looney Tunes. Cartoons exempted. The cannonball goes flying because its mass is smaller. Therefore, the downstairs of the fraction is smaller. Therefore, the fraction itself is a bigger number. As the mass gets smaller, if you have the same force, third law of force, equal force, smaller mass, bigger acceleration. The cannonball goes flying. The cannon stays, well, can't stay exactly in place. There's always recoil, but moves much less. Turn to your neighbor and discuss real fast. Ask me a question. Let's bring it together. Yami, please. Yes, exactly. If you go out to the playground and shove a 5-year-old and then shove a parent with the equal force, I don't know which is going to get you a bigger punch in the nose, but the 5-year-old goes flying. Why? Because a bigger mass would require a bigger force. If you apply the same force, the small thing goes flying, the little thing doesn't. The cannonball pushes on the cannon. The cannon pushes on the cannonball. These are third law pairs. The force magnitude is guaranteed to be equal, so the bigger mass doesn't recoil as much. It's got more inertia. Okay. Question M. Let's see, how about this? You may notice a theme, by the way. Once this clicks, this gets easy, but let me see if it's clicked yet. I encourage you to look at your notes, by the way, because I've told you the answer to this. Also, turn to your neighbor and discuss which law of physics are we talking about in this problem. They will be, as soon as I'm able to log in. Okie dokie. The question asks, which force, when bug pushes window and window pushes bug, which force is bigger? Correct answer is, these are third law pairs. Force pushes bug, bug pushes force. C, they are equal forces. Third law pair, bazinga. Now let me ask you this. If I go and boop your snoot with my finger, and then go and boop, but no, that's too small to really get a feeling for. If I go and flick a marble and then flick John Cena, is the same thing going to happen in either case? Right? The marble's going to go flying, and I guess ultimately in the second case, I'm going to go flying too. So just exerting the same force on a different thing doesn't mean you get the same effect. You exert a little pushy on a mosquito and you crush his little bones. Do they have bones? They don't have bones. Whatever, you crush them. You push with the same force on a car and it doesn't crush. But again, which force is bigger? Neither. I'm exerting the same force on different things. Google form N. Read carefully. And talk to your neighbor. There is a law of physics. Which law of physics, law or laws, are we using here?
So, essentially what you're looking at, the same rule we talked about before. And then have because they're exerting the same amount of force against you. Yeah, because, well, if they're pushing off each other, that means
There is only one correct answer. You cannot say something or something. Doesn't matter who's pushing. The push is the push is the push is the push. Okay, so now we are at 3/4 wrong. We're at a quarter pounder of correctness. Turn to your neighbor and give him a high five. You give them a high five and then switch. And turn to your neighbor. First, you give them a high five, then they give you a high five. Let me ask you this. Did it feel different when you gave versus when you got? Is it possible to slap hands either way and have one hand feel it and the other hand not? B is irrelevant. There is no push equally. There's always a push equally. Third law pairs. It doesn't matter whose arms extend. The hand on hand is hand on hand is hand on hand. A pushes B, B pushes A. It doesn't matter whose arm is moving at all. If skater 1 pushes skater 2, then they have to have the same force. And if they have the same force and equal mass, what else do you know? You're going to have the same acceleration. The correct answer here is A. There is no such thing as exerting different pushes. Question me. Try it with your classmate. Turn to him and you give him a strong high five, preferably not on the broken arm. That was extra hard. Okay, tell me, did you feel it both times? Okay, you give her a high five. Now an extra hard high five. Did you feel it both times? It doesn't matter whether it's a big force or a little force. It doesn't matter that your arms are extending or his arms are extending. If there's an interaction between two objects, the force is the force is the force is the force. You interact with him, he is interacting with you. Exactly the same amount. Yeah. Yeah, utterly irrelevant. Well, if they were on, if one person's on ice and the other person's on the shore, on grass or whatever, then the force will still be equal, but the person on ice only has one force on them. They're going to move the person on the ground. Well, the person on the ground, I'd say you plant your feet and you're not going to move backwards. You'll feel the force, but there's another force, a friction force on your feet. Just because there's a force doesn't mean you accelerate. There has to be a total force. And if you plant your feet, look, I mean, here.
Same speed. Like
if they have the same acceleration over the same time, they have the same final speed. If the accelerations are the same and the times are the same, then the velocity change will be the same. Okay, so again, I want to emphasize this. B is wrongo. Wrongo, 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 wrongo. There is no only. This always happens, unavoidably. Let's get fruity. Let's get fruity. I want to talk about system for a sec. And when third law is important to use and when you can't use it. Suppose I put my son, an orange, in a cart and pull him with a rope. I apply an external force. We'll assume that the cart is not as crappy as... By the time my kids play with toys, they exert significant friction forces. Suppose we got good wheels here. You exert a force on the rope, the orange cart system is going to accelerate. If I consider orange and cart as my system, I can draw a dotted line around the system. The pull of the rope on the wagon is the only significant horizontal force. That's the only force I need to consider. I don't need to ask if there is a force on the rope on the puller, on me, because that's on something that I don't care about. If I am asking a question about the acceleration of this system, don't tell me about forces on something else. Unless I specifically ask you, what's the force that it exerts? Okay, now, action and third law pair force, the fact that the apple pulls the orange, therefore the orange pulls back on the apple. That is a third law pair. You cannot have a taut rope. You cannot pull on one end of the rope without the other end feeling the same force. Action and reaction do not cancel because this sucker does not feel the force on that sucker. If A pushes B and B pushes A and they're in opposite directions, that doesn't cancel because they apply to different objects. Forces that orange exerts on apple are not felt by orange. So they do not cancel. Those forces are on different objects, they do not cancel. The external force of the rope tension on the cart accelerates the orange. Now let's imagine we draw a dotted line around both of them, me and my son. The apple is now part of the system. And what did I tell you very first when you're talking about Newton's third law? You can't change the position, you can't accelerate, you can't move your own center of mass. So the apple pulling on the orange and the orange pulling on the apple, that force is not accelerating the system. What does accelerate the system is the fact that the apple's feet have traction on the ground. There is a force of ground on system. And that's a different force than this tension force. In fact, it's a bigger force than this tension force. It has to be a bigger force than this tension force because this force is moving two objects and this force is moving one object. And regardless of how you look at it, the answer better come out to the same acceleration, right? It can't matter what you're considering. What you're considering can't affect what its acceleration is. So big dealio, Julio. Big dealio is that if we consider one object to be a system, then forces that it exerts on other objects, not relevant. If you consider two objects for the part of the system, the third law of pairs are forces of A on B, B on A. B and A are the same thing. Forces of A on A cancel forces of A on A. You never consider third law of pairs within a system. This pulling force, if you just had this pulling force and no other force, this rope force would pull the apple and the orange together and their center of mass would not move. Their average position, sort of, would not move. It's only the fact that apple has traction on here that means that apple is able to run, and that traction is what accelerates the whole system. Okay, so if we consider the external force of friction, that is a different force, and that's the only external force that we can care about if we're trying to calculate the acceleration of the apple-orange system. Apple-orange system has no tension, external tension. Moral of the story here, let me summarize here. Moral of the story, identify your objects. If your objects have parts, then don't tell me about the force that one part exerts on the other. Internal forces cancel. If we're talking about two different objects, then third law of pairs never cancel. Third law of pairs are on different objects. They never cancel because they're on different objects. Not on one thing, not pushing and pulling on the same thing. Turn to your neighbor and express those two sentences to each other. Real fast. You got a physical example right in front of your eyes? Take a look. I got a ball. I got a ball right here, bowling ball. I kick the ball. Do I care if I talk about the bowling ball? Does my friction have anything to do with it? The ground, I've got good traction. I kick the ball. Does the force of ground on me, do I have to care about that if I'm looking at the ball? Yes or no? Give me at least a shake of the head or a nod of the head. No. Forces on me are irrelevant to forces on the ball. Now, if this were slippery rug, you could see that I have to recoil a little bit. As it is, the traction that I get, the friction that I get from the ground means that my center of mass is not moving. But I will tell you that I've moved part of this system, if I consider system as both of us, part of this system that way. I moved it that way, and that is not possible to calculate just from the interaction force, you also have to consider the ground if we're talking about something external to both objects. We'll come back to this one. I feel like we need to do some problems before this is making you smile. No, let's get that one. No, let's get that one. No, let's get that one. Okay, I told you this yesterday class. I showed you at the very end of class. Let's see if you remember something. This will be questions OPQ respectively. So let me write that down. This is Google form, Google question O. O for oh my God. Oh, for dog's sake. Why? D is not possible. I'm asking you to identify either normal or weight force. For question O, anyway. Better. For P, there's a hint. How hard does the ramp push on the object now? If I raise this all the way, how hard is the ramp pushing on the object? Did that get bigger or smaller? Hint, hint, hint. There's another thing. Google question Q is asking for not the acceleration, but the force on the block. Give me an equation or something that you could use to calculate the force on the block. If you tell me in units of meters per second squared, you are telling me an acceleration. I don't want acceleration, force. Or if there's no force, you could tell me that. Again, I'm not looking for A. Don't tell me A. That's not what the question asks for. Tell me about force. How can I find the force inserted on the vertical block, on the block with the table next to it? G sine theta is wrongo. Again, G sine theta tells you an acceleration, tells you how rapidly something accelerates. You can plug into that formula and find the acceleration of the block when the table is vertical. That's good, that's great, that's not what I'm asking. I want you to tell me, how would you find the force on the block? It is written directly on the slides, by the way. Again, let me point this out to you. The forces on the block, normal and weight force, are written right there. If I'm asking for the total force on the block when the angle is vertical. Look at the slide carefully. Okay, time's up. The correct answer is mg, because it says so right here. Normal force represents what I said last class, represents pushes at right angles to the block. If the block is just falling beside the ramp, is the ramp pushing it that way? No. Here, let's test this hypothesis. I'm going to drop this, and y'all tell me if the paper towels are launched to that side of the classroom. Ready, set, real difficult experiment here. Oh my God, they weren't launched that way. The table does not push on it that way when it's falling down, when the paper towels, oh, I said it, when the paper towels are falling down, yeah? Okay, so the only force on it is what? Weight force, gravitational pull of the earth on the towels, yeah? Okay. Hey, yeah, so correct answers here are the force that remains constant is weight, mg, gravity. The Earth's gravitational pull doesn't care what you do with ramps and stuff. Gravity is gravity is gravity. That never changes unless you get into a rocket. The correct answer for the second thing is, well, consider this. Normal force is completely opposing weight force. Normal force is equal and opposite to weight force. Does that make it a third law pair? No. No, just because two things are equal and opposite does not mean they satisfy the criteria to be the equal and opposite third law pair forces. Watch out. We're going to review that more big time. Okay, normal force is big. It's entirely opposing mg. Look at the arrows. They get smaller and smaller and go to zero. If you just consider the extrema, the minimum and maximum cases, when the angle is 0, there's a big force. When the angle is 90, there's no force, normal force. So the correct answer for P is it decreases. And the correct answer for Q is mg, weight, gravity. Okay, one more point. I want to make one more point. Google form R. What do you think? Take a stab at it. This is very important in the homework, by the way. I think there's 1 problem, 3 problems. Good. Now, one more minute. You all can get this. Yes or no? Chop, chop. Exactly. Okay, so reflect on this, my grasshoppers. What did I tell you about G? G is gravitational field strength. What did I tell you? G is 9.8 everywhere in the universe? No, G is 9.8 meters per second squared, 9.8 newtons per kilo. Anywhere on the surface of the Earth where humans live, and within the biosphere, G is 9.8. G, little g, is not a universal constant. On the moon, G is 1.6 something meters per second squared. Okay, on Mars, it's 3 point something that I forget meters per second squared. G is not a universal constant. It depends on where you are. If I give you a problem and don't specify outer space, you can assume that I'm talking about the Earth, and you can plug in G equals 9.8. If we're talking about on the moon, your mass, does your mass change? No. How much of you there is, I mean, unless you vomited on the rocket ride, how much of you there is doesn't change just based on where you are, but how hard the planet or moon or star or whatever pulls on you does. I think I have hit everything you need for the midterm and the homework problems that I'm going to include next week We're going to definitely hit on Monday. We're definitely going to do more examples of the third law because I think that is wrecking you. But you are now done for the week. Ready, set, go. Have fun going to bed. Yes. As soon as I can access my ASU again, it'll be Friday at least. Sorry.